Welcome all to another exciting special problem. Today we're going to look at chapter 11. Okay, so this one is about air pollution. Okay, they're talking about the way that they're going to measure the air pollution. They're measuring it in a city and a rural location, 10 miles apart, on the same days. There are some days where they don't have readings because equipment failure. Okay, so here's our data. And down here we're talking about equipment failure should be fairly random. So we're able to basically take the days we have readings and consider that to be a random sample. So we should have bias-free data here. Okay. Question A. Assess the level of particulate pollution in the city. Describe the distribution. Estimate the mean. So in other words, give a confidence interval. All right, so step one, you need to get the data into your calculator. And I have the city data here in my list one. Okay. So to describe the distribution, we're going to want to make some graphs. So first graph, I always go to the modified box plot. So modified box plot, list one. And there we go. So things look fairly symmetric with two outliers on the right. Okay, so put that on your paper. Okay, and of course use your trace key to actually get these values. So minimum is 30. First quartile is 44. Median's 50. Third quartile is 60. Highest point that's not an outlier is 82. And then we have outliers of 90 and 120. Okay, so let's do some one variable stats on this. And there we have it. Letter A. X bar is 56. Q2, as we mentioned, is 50. S of X, approximately 18.8. But again, when I use this, I'm not going to use 18.8. I'm going to use the value that's saved in my calculator. N is 31. Okay. So we're going to be making a confidence interval here. Here's the summary statistics that I'm going to be needing. Here's my modified box and my sample size. So we need to validate this. Okay. Well, step one, do we have good data? We talked about that earlier, right? We can consider the days where the equipment failed to be random chance. So the remaining data we can see as unbiased random data. So we can consider the data to be random and free from bias. Okay, next, we're going to use standard error formula in this situation. Population size, at least 310. Yes, we're talking about a city, right? I'm sure the city has been around for 310 days. Okay. Oh, I forgot to mention the population of interest. Okay, this would be pollution in the city center. Okay, and you could get more specific, particulate, whatever, but pollution. Okay, so the city's been around at least 310 days. So our sample of 31 is not more than 10 times, not more than 10% of the population. And of course, we're using the standard error formula because we do not have sigma. Okay. All right, last requirement of the test is normality. We do have 2 outliers, so that could be a problem. Let's go ahead and do a normal probability plot just to follow up. And there's our normal probability plot. Okay, so hopefully at this point you're starting to feel comfortable that sample size of 31, that's fairly linear. And yeah, we have some outliers, but we don't really have heavy skewness, so we should be safe in calling this normally distributed. Okay, but we should still mention with 2 outliers. And a fairly symmetrical distribution. We should be safe. Assuming a normal distribution. So basically green lights, right? No real issues. So this is when you would not say proceed with caution because we're looking pretty good. All right, so now we're going to be calculating a confidence interval. Notice they didn't tell me a confidence level, so it's up to us. Now, if this happens on a test question, obviously don't pick a 57% confidence level, right? That would just be silly. Pick one of the common ones, 90, 95, or 99. Now, of course, the most common is 95, so that's the one I'm gonna pick. So let's make a 95% confidence interval. Okay, so it's our statistic, plus or minus, our critical value, and of course, I didn't bring my table, so let's see if we can do an inverse t here, and we're trying to do a 95. So let's do 0.975, right? Because remember a 95% confidence interval. 95% in the middle, 2.5s on either side. So right there is my critical T at the 97.5th percentile. Okay, my degree of freedom would be 30. And there we go. And I want to say that looks pretty familiar. If you use your table, I'm pretty sure you get 2.04. So, or maybe even 2.042, something like that. Okay, and that gets multiplied by our standard error, which again, I'm gonna write, 18.8 over the square root of 31. Okay. But I'm not actually gonna use that, right? At this point, I'm gonna use the calculator. So this is a T interval. We have data, it's in list 1, and let's do a 95% confidence. And there we go. So about 49.1 to 62.9. Okay, now remember your conclusion. We are 95% confident. Right? Every conclusion needs to tell the confidence level. Now we need some context. So that the true mean particulate level in the city center is between 49.1 and 62.9. What are the units on this? Yeah, I don't see the units. Weigh the filter, but I'm not sure if it's in grams or, so we'll just say units. All right, so there we go, confidence interval. Okay, on to question 2, question B. Okay, here we want to compare the mean level of particulate in the city with the rural, this is real important, on the same day. That right there tells me it's dependent. They're 10 miles apart, air moves, right? So we're wondering if the air, if you read the problem, right? If the air and the wind is blowing more pollution in one direction or the other. And in this case, we're wondering if we're getting more pollution in the city, okay? So, step 1, we gotta get the data. We need to check our requirements to make a valid calculation. Okay, so it's on the same day, which means anytime you have only one of the 2 readings, you can't use that, right? So we're only going to be using the days where we have readings for both, okay? Because I can't do NA versus 52 and subtract that, and I have no idea what that is, okay? So just go through the list and find all of the days where I have both readings, okay? And subtract them, right? Because we're trying to figure out, do I have more pollution on average in the city? Okay, so this is a matched pairs design. Okay, so again, I have that data in my calculator. Okay, that's in my list 2. So on the first day where we have readings for both, the city had 10 more units of pollution. On the second day that they both had readings, the city had 2 more units, so on and so forth. Okay, so there's my list 2. All right. So again, population of interest. and this would be the difference in pollution levels between the city and rural locations on the same day. Okay. So we now need to do our checks. Okay. We already mentioned the whole, we can consider the data to be an SRS. We'll go ahead and mention it again. Well, not necessarily an SRS, but a random sample, an unbiased random sample. And now population size. Again, we're talking about the Earth. So we know we've got plenty of days where there's been a city and a rural location that was 10 miles southwest. So we clear that hurdle. Okay, and now the final hurdle, we got to make a graph. So again, the graphs I like are the modified box because it tells me outliers and skewness, and the normal probability plot. So that's what I'm going to do. Modified box of list 2. And this time we do have one outlier on the left, but boy, oh boy, it looks pretty darn symmetrical, and that outlier's really not that extreme. Okay, so let's put it on our paper though. Okay, and put our values. Outlier is -6. -4. Quartile 1 is 2. Median is 4. Quartile 3 is 6. So yeah, it's pretty darn symmetrical, right? I mean, we're 8 units from the median to that, and we're, what is that? 10 units the other way. So it's symmetrical. I'll go ahead and follow up with a normal probability plot, but we're looking good. Yeah, so that's pretty darn linear. But we should still mention the outlier, and also don't forget to do our one variable stats here. Okay, notice our sample size is less, right? Because any day where either equipment didn't work, we couldn't use. So a little smaller sample size, but aside from the one mild outlier, we're very symmetrical. So we're safe. Okay, with one small outlier and a symmetrical distribution. We are safe to assume a normal distribution of differences. Okay, so again, green lights. No need to proceed with caution. We should have a good calculation here that we can trust. Okay, now let's carry out our significance test. So, null hypothesis. The mean of the city minus the rural, 0, meaning there's no difference. They're the same. Now, careful. This is a matched pairs test, right? That's why a lot of students miss this on not just this problem, but this unit. They do checks on both data sets. Well, I'm not interested in that. I'm interested in the difference on the same day, right? Dependent data, matched pairs. Same thing with the hypothesis. There's only one mean difference, okay? But a ton of students write, mu1 minus mu2 or mu1 equals mu2. No, that's wrong because this is not a 2 sample. It's a 1 sample. Okay, alternative. When I take the city minus the rural, I get a positive mean. Okay. All right. Oh, I don't think I wrote down my, there we are. So there's my X bar. .85 approximately. Sample standard deviation, approximately 4.9. Okay, and in 26. Okay, so a degree of freedom of 25. All right, let's calculate our test statistic. So we want to know the probability of X bar being greater than 3.85, which is the probability that T is greater than 3.85 minus 0 divided by, what do we have here? 4.9 over the square root of 26. Okay, and now we just use the calculator. T-test, data, list 2. And there's our T, roughly 4. And of course, when you have a T statistic of 4 with a reasonable size sample, you're going to get a small p-value. So our p-value is small. 2.4 times 10 to the negative 4th. Okay, remember this is scientific notation. So, conclusion. Notice, again, they didn't give me an alpha. You could say add an alpha at 5% if you want, but I'm going to use the modern approach with a p-value of 0.0002. We have very strong evidence to conclude the pollution in the city is higher or greater than the pollution at the rural location on the same day. Okay, notice if they hadn't put that on the same day bit into the problem, then a 2 sample could be used, right? But again, read carefully. That's the key. Oh, there's a follow-up. It says also estimate the mean amount by which the city particulate level exceeds the rural level on the same day. So we need to do a confidence interval here. Okay, we already did our checks, so we're good to go. So what was our X bar? I'll just pull this here. Our X bar was 3.85. Plus or minus. Again, we need our T star. Oh, distribution, inverse T. I'm going to do a 95% again. And our degree of freedom here is 25. Okay, and you can see we get a little larger T star because our degree of freedom is less than the last problem. And that's going to get multiplied by 4.9 over the square root of 26. Okay, and now calculate. T interval, list 2. And there we go. Okay, and our conclusion. We are 95% confident the city pollution level exceeds the rural location on the same day by 1.87 to 5.82. Again, units. I'm not sure what the units were. Okay. All right. Final question. We hope to use the rural particulate level to predict the city level on the same day. Okay. Make a graph. All right, so in this instance, we're actually going way back to chapter 3 and 4, right? We're looking at city versus rural on the same day. So we're going to need to put that info in our calculators. And I have it here. So list 3 would be the rural, list 4 is the city. And again, we're only looking at days where we have readings for both. Okay, so our graph would be a scatter plot here. And I've got list, I've got list 3 and list 4. And there's your scatter plot. So again, put that on your paper. But also notice, that is looking pretty linear, isn't it? Pretty strong relationship. Okay, something like that. This is rural, city. Okay. All right. So again, I'm just kind of throwing enough out there that you can look at it and go, oh yeah, it looks pretty linear. Pretty strong positive association there too, right? Okay. So there's our graph. Does the graph suggest using least squares regression will give approximate correct results? I would say so, yes. The scatter plot does seem to suggest a strong positive linear association. Okay. All right. Now let's calculate the least squares line. Okay, stat len reg. Let's see, list 3, list 4. And yeah, let's go ahead and store that. And there we go. And sure enough, a pretty strong correlation right there, right? So my hat, approximately 1.06 x plus 0.93. And we have a correlation of approximately 0.97 and a r squared of approximately 0.94. Okay. What percent of the variation does the straight line relationship account for? Oh, right there. Approximately 94%. Oops, I wrote 95. 94% of the variation in the city's pollution can be explained by the straight line relationship with the rural pollution level on the same day. Okay. On the 14th date, the rural reading was 88. City reading was not available. What do you estimate? Okay, before we actually do any predictions, remember we should always do residual plot. So let's do that real quick. Okay, so our residuals, the observed y minus the predicted y. So let's see, that's list 4 minus y1 of list 3. Okay, so there's my residuals. Let's make my residual plot. So list 3, list 5. There's my residual plot. So I'm gonna throw that on my graph real quick, my graph on my paper. Something like that. And looks good, right? The residual plot shows random scatter. So the least squares regression line should be a good model to predict the, what was this, the 14th day? Yeah. Missing city value on day 14. Okay, so let's do it. Take your equation, put 14 in there. Day 14 for the rural was 88. Okay, so should get that, approximately 94. Okay, make sure to answer this in a sentence. Okay, we predict the day 14 reading in the city to be approximately 94. Okay, now remember, we don't stop there. We need to say, hey, do we think this is a good prediction or do we think it's pretty weak? In this case, we had looked like a nice linear relationship. Our residual plot confirmed. We have a strong R. And very importantly, we are doing interpolation. So we should have a good prediction here. So with a strong correlation of 0.97, a random scatter in our residual plot. Whoops, residual plot, and doing interpolation. We feel confident in this prediction. Okay, so that was nice. We got to do a little bit of a review from chapters 3 and 4. We're going to be hitting this again in chapter 14. We're going to do inference on predictions, so that's kind of why we're throwing it back out there to refresh your memory. Okay, hopefully you're doing this before our test, and hopefully it's all making sense, and good luck then on your test.